There's a place on this planet where the ocean floor opens its mouth and swallows everything whole. Light, sound, time, and sometimes the people brave enough to look inside. Off the coast of the Bahamas, scattered across shallow turquoise water like dark bruises on skin, lie hundreds of perfectly circular holes punched into the seafloor, some barely wider than a swimming pool, others stretching 100 meters across, all of them dropping straight down into a blackness so complete that even the most powerful dive lights cannot reach the bottom. From above, from an airplane window or a satellite image, they look almost decorative. Deep blue coins pressed into the pale, sandy shallows. Beautiful, geometric, almost artificial, as if some ancient civilization drilled them with purpose. But the moment you slip beneath the surface and begin to descend, the beauty dissolves into something far more primal, something that triggers a very old part of the human brain, the part that whispers, "Turn back, you do not belong here." These are the Bahamas Blue Holes, and they are arguably the most scientifically important, most geologically complex, most biologically alien, and most lethally dangerous underwater environments ever discovered on Earth. What lives inside them defies everything we thought we knew about where life can exist. What rests on their floors has been preserved for 10,000 years in conditions that mummify bone and wood and ceramic with a precision that no museum could replicate. And what their walls and water chemistry tell us about the early history of our planet, and possibly the future of our search for life beyond it, is so staggering that NASA has taken notice. But before we go down, before we cross the boundary that separates the world we know from the world that has never seen sunlight, you need to understand what these holes actually are, how they formed, and why the Bahamas of all places on Earth became the single most concentrated collection of them anywhere on the planet. Because the answer to that question takes us back 20,000 years to a world so different from our own that it would be almost unrecognizable. A world of ice and exposed rock and rivers of rain-carving labyrinths into limestone at a geological pace, drop by patient drop, century by century, building a trap so perfect that it is still claiming lives today. 20,000 years ago, at the peak of the last great ice age, the planet looked nothing like it does now. Vast sheets of ice, some of them 3 kilometers thick, blanketed North America and Eurasia, locking away so much of the world's water in frozen form that global sea levels dropped by approximately 120 meters below where they sit today. 120 meters. That is not a number that is easy to visualize. So think of it this way. If you could drain the modern ocean by that much, the Bahamas would not be islands at all. They would be a high limestone plateau rising above a flat, semi-arid landscape, a place where animals roamed freely, where rivers ran through valleys, and where the rain, slightly acidified by carbon dioxide absorbed from the air, fell on exposed rock and began one of the slowest and most consequential chemical reactions in the natural world. Limestone, which is what the entire Bahamian archipelago is made of, is calcium carbonate. It is technically soluble in water, not quickly, not dramatically, but given enough time and enough slightly acidic rainwater, it dissolves. It does not dissolve evenly or uniformly. It dissolves along fractures, along bedding planes, along the paths of least resistance, and over thousands of years those paths become channels, and those channels become passages, and those passages branch and widen and deepen until the rock is no longer solid at all but a 3-dimensional labyrinth of chambers and corridors and vertical shafts, some barely wide enough for a human body to squeeze through, others opening into rooms the size of cathedrals. This process is called karstification, and the Bahamian limestone, which formed over millions of years from the compressed remains of ancient marine organisms, is exceptionally pure and dense in some places, and exceptionally porous and layered in others, which is why the cave systems that formed inside it are so wildly varied in their architecture. Some developed as narrow vertical shafts, dropping almost perfectly straight down for 100 meters or more. Others spread horizontally, growing into vast networks of interconnected rooms and tunnels extending for kilometers in every direction beneath the surface. And all of this happened in the open air, exposed to the sky, filled with the bones and footprints of the Ice Age animals that lived above. Then, around 12,000 years ago, everything changed. The ice began to melt, slowly at first, then with increasing speed, the glaciers that had locked up so much of the planet's water released it back into the ocean. Sea levels rose, and the Bahamian plateau, with its thousands of caves and sinkholes and vertical shafts, began to flood. The ocean crept up the valley walls and over the limestone ridges and down into the cave entrances, filling them from the bottom up, sealing everything inside in salt water, covering the bones of the animals that had fallen into the dry caves during the Ice Age, preserving them in a chemical environment so stable and so oxygen-free that they would remain essentially unchanged for the next 10,000 years, waiting for a species equipped with tanks and lights and an insatiable curiosity to come and find them. That is how the blue holes were born, not carved by the ocean, but drowned by it. The ocean did not make these caves, it inherited them, and that distinction matters enormously because it means that everything inside these flooded limestone systems is a time capsule from a world that no longer exists, a sealed record of Ice Age ecology and chemistry preserved with a fidelity that no other environment on Earth can match. Today, the island of Andros alone, as the largest of the Bahamian islands, contains an estimated 200 partially explored blue holes, and geologists believe that the actual number, including those that have not yet been found or mapped, could be significantly higher. Across the entire archipelago, the count runs into the hundreds. No other place on Earth has a comparable concentration of these formations, which is why the Bahamas have become the global center of blue hole. Research, drawing scientists from oceanography, geology, paleontology, microbiology, astrobiology, and archaeology, all of them chasing different pieces of the same extraordinary puzzle. But to understand what makes these environments so scientifically extraordinary and so viscerally dangerous, you have to understand what happens to the water inside them, because the water in a Bahamian blue hole is not uniform. It is not simply seawater filling a cave. It is a layered system of radically different chemical environments stacked on top of each other like the floors of a building, each one with its own temperature, its own chemistry, its own biology, separated by invisible boundaries that the laws of physics enforce with absolute authority. If you were to dive into a typical blue hole off the coast of Andros on a calm morning, your first 15 or 20 meters would feel relatively familiar. The water would be clear, warm, lit from above by diffuse sunlight filtered through the surface. You would see fish moving along the cave walls, algae in the shallower sections, perhaps a small shark investigating your presence with the casual confidence of a creature that has never had a reason to fear anything. It would feel, if not comfortable, at least comprehensible. Then, at somewhere between 20 and 30 meters of depth, depending on the specific hole and the time of year, you would encounter something that looks, at first, like a hallucination. Stretched across the full width of the cave, from wall to wall, with no gaps and no way around it, floats what appears to be a liquid mirror, a shimmering, undulating surface that reflects your dive light back at you like polished silver, bending and warping the beam into strange interference patterns, making the water below it look like a pool of mercury. This is the halocline. It is the boundary where fresh water, which is less dense and floats on top, meets the denser, colder, heavier salt water that fills the lower reaches of the cave. The two layers do not mix, not significantly, not spontaneously. The density difference between them is enough to maintain a sharp, stable boundary, and that boundary, that shimmering optical illusion, is one of the most disorienting things any diver can encounter, because when you push through it, when you break the surface of the halocline and enter the saltwater layer below, everything changes at once. The temperature drops sharply. The water feels different against your skin, denser, almost thick. Your buoyancy changes, and your vision, already challenged by the low light, is now further distorted by the optical mixing of two water types with different refractive indices, making everything appear slightly blurred and unstable, as if the world itself has become uncertain. Below the halocline, the real mystery begins, because below that shimmering boundary, the salt water is not simply cold and dark. It is, at depth, completely devoid of oxygen. The water in the lower sections of these caves has been isolated from the surface for so long, in some cases for thousands of years, that every molecule of dissolved oxygen has long since been consumed by bacterial respiration. What remains in its place is hydrogen sulfide, a toxic gas produced by anaerobic bacteria as they break down organic matter. The same gas that gives rotten eggs their characteristic smell, but here present in concentrations that would be immediately dangerous to any air-breathing organism. In many blue holes, this hydrogen sulfide does not simply dissolve invisibly into the water. It forms a distinct visual layer, a dense, cloudy, faintly yellowish-green cloud that hangs in the water column like smoke, sometimes several meters thick, hovering at a consistent depth below the halocline. Divers who have pushed through this layer describe it as entering a different dimension. The water turns murky and strange, the visibility collapses, and there is an almost physical sense of wrongness, of being somewhere that was never designed to accommodate a human being. For them, it is a warning zone, crossed only with full protective equipment and an acute awareness of time. But for the bacteria that live there, it is paradise. What those bacteria represent is one of the most scientifically compelling aspects of the entire blue hole system, and one of the main reasons that researchers keep descending into these dangerous environments year after year. The organisms that thrive in the anoxic depths of Bahamian blue holes are not ordinary life. They are extremophils, microorganisms adapted to conditions that are lethal to virtually every other form of complex life on Earth. In the complete absence of oxygen, in water saturated with toxic hydrogen sulfide, in perpetual total darkness, they not only survive but flourish, forming thick mats on the cave walls and dense suspensions in the water column, building entire ecosystems on the chemical energy released by sulfur metabolism, a process called chemosynthesis. These bacteria do not need sunlight. They do not need oxygen. They extract energy directly from the chemical bonds of hydrogen sulfide, oxidizing it and releasing sulfate as a byproduct. It is one of the most ancient metabolic pathways known to science, and the reason that is so important is that it connects these cave-dwelling microbes to the very origins of life on Earth. When the first living organisms appeared on this planet roughly 3.5 to 4 billion years ago, the Earth's atmosphere contained almost no free oxygen. The oceans were rich in sulfur compounds. The chemistry of early Earth looked, in many respects, remarkably similar to what you find at the bottom of a Bahamian blue hole today. Vast networks of interconnected rooms and tunnels extending for kilometers in every direction beneath the surface. And all of this happened in the open air, exposed to the sky, filled with the bones and footprints of the Ice Age animals that lived above. Then, around 12,000 years ago, everything changed. The ice began to melt, slowly at first, then with increasing speed. The glaciers that had locked up so much of the planet's water released it back into the ocean. Sea levels rose, and the Bahamian Plateau, with its thousands of caves and sinkholes and vertical shafts, began to flood. The ocean crept up the valley walls and over the limestone ridges and down into the cave entrances, filling them from the bottom up, sealing everything inside in salt water, covering the bones of the animals that had fallen into the dry caves during the Ice Age, preserving them in a chemical environment so stable and so oxygen-free that they would remain essentially unchanged for the next 10,000 years, waiting for a species equipped with tanks and lights and an insatiable curiosity to come and find them. That is how the blue holes were born, not carved by the ocean, but drowned by it. The ocean did not make these caves, it inherited them, and that distinction matters enormously because it means that everything inside these flooded limestone systems is a time capsule from a world that no longer exists, a sealed record of Ice Age ecology and chemistry, preserved with a fidelity that no other environment on Earth can match. Scientifically compelling aspects of the entire blue hole system, and one of the main reasons that researchers keep descending into these dangerous environments year after year. The organisms that thrive in the anoxic depths of Bahamian blue holes are not ordinary life. They are extremophils, microorganisms adapted to conditions that are lethal to virtually every other form of complex life on Earth. In the complete absence of oxygen, in water saturated with toxic hydrogen sulfide, in perpetual total darkness, they not only survive but flourish, forming thick mats on the cave walls and dense suspensions in the water column, building entire ecosystems on the chemical energy released by sulfur metabolism, a process called chemosynthesis. These bacteria do not need sunlight. They do not need oxygen. They extract energy directly from the chemical bonds of hydrogen sulfide, oxidizing it and releasing sulfate as a byproduct. It is one of the most ancient metabolic pathways known to science, and the reason that is so important is that it connects these cave-dwelling microbes to the very origins of life on Earth. When the first living organisms appeared on this planet roughly 3.5 to 4 billion years ago, the Earth's atmosphere contained almost no free oxygen. The oceans were rich in sulfur compounds. The chemistry of early Earth looked, in many respects, remarkably similar to what you find at the bottom of a Bahamian blue hole today. The danger of blue hole diving is not a matter of bad luck or lack of preparation. It is structural, built into the physics and chemistry and geometry of the environment itself, and it has claimed the lives of experienced, skilled, well-equipped divers who made small errors in places where small errors are not survivable. The first layer of danger is orientation. Inside a flooded cave, there is no ambient light. There is no surface visible. Above you in most directions, no reference point that can tell you which way is up if you become disoriented. When you pass through the halocline and enter the turbid, chemically active layer below it, visibility can drop to near zero almost instantly. Your dive light, which seemed powerful at the surface, may penetrate only a meter or two into the murk. In that darkness, in that enclosed space with passages branching in multiple directions and dead ends waiting at the ends of many of them, it is possible to become comprehensively lost within minutes. The cave systems connected to these holes are not small. Some extend for several kilometers, passages narrow and widen unpredictably. Rooms open into rooms that open into more rooms, and without a continuous line, the thin, brightly colored guideline that experienced cave divers always deploy. There is no way back. Divers who have run out of line and had to turn back have reported the particular terror of swimming through black passages with no visual confirmation that they are moving in the right direction, trusting entirely to compass and memory and the metronomic counting of their remaining air. The second danger is nitrogen narcosis. At depth, the nitrogen in compressed breathing air dissolves into the bloodstream under pressure and acts on the brain in a way that is, neurologically, surprisingly similar to alcohol intoxication. The onset is gradual, and the symptoms are insidious. A growing sense of well-being, a reduction in anxiety, impaired judgment, a tendency to ignore warning signs that should trigger immediate corrective action. Divers have described the feeling as a warmth, a comfort, a sense that everything is fine, even when the objective evidence clearly indicates otherwise. At the depths accessible in some Bahamas Blue Holes, 60, 70, 80 meters, narcosis is not a mild inconvenience. It is a serious cognitive impairment. Decisions made under its influence have sent divers deeper when they should have ascended, have caused them to miss turns on their return route, have made them linger at depth past the point where their gas supply allowed for a safe return to the surface. The third danger is the sediment itself. The floors of these caves, undisturbed for thousands of years, are covered in a layer of extremely fine silt, a mixture of organic particles, bacterial biomass, and the powdered remains of dissolved limestone, accumulated over millennia in completely still water. It is lighter than talcum powder, and it responds to the slightest water movement with explosive immediacy. A careless kick of a fin, a hand placed on the floor for stability, even the turbulence from a diver's exhaled. Bubbles rising to the ceiling and disturbing the silt deposited there. Any of these can instantly transform a space of moderate visibility into a total whiteout, a cloud of suspended particles so dense that a diver literally cannot see their hand in front of their face. In a whiteout, in an enclosed space with no visual reference to indicate which direction leads to the surface, the most experienced diver in the world is in serious trouble. The instinct is to swim upward, but in a complex cave system, upward may lead directly into the rock ceiling. The correct response, stay still, wait for the silt to settle, trust your guideline, requires a level of calm that is genuinely difficult to maintain when you are breathing compressed gas at depth in total darkness in a flooded cave, and you have no idea where the exit is. The combination of these hazards has made Bahamas Blue Holes one of the leading sites of dive fatalities worldwide over the past several decades. The roster of those who have died here includes men and women with thousands of hours of underwater experience, instructors and researchers and explorers who knew exactly what the risks were and chose to accept them because the scientific and historical value of what lay inside these caves seemed worth the price. Some of their bodies were never recovered. The caves kept them, but the research continues. Each year, new expeditions descend into these systems with better technology, rebreathers that dramatically extend dive duration and eliminate the bubbles that disturb silt, high-resolution mapping sonar that can chart passages too narrow or dangerous for a human diver, underwater remotely operated vehicles that can push further into unexplored sections than any person could safely go. And each year, new discoveries emerge, new species, new fossils, new archaeological finds, new data about the chemical evolution of the early Earth, new clues about what life might look like on the dark, pressurized, chemically complex oceans of the outer solar system. The Bahamas Blue Holes are not a finished story. They are a story that has barely begun to be told, a record of 4 billion years of planetary history compressed into a series of dark, circular holes in a shallow tropical sea, sealed by the rising ocean at the end of the Ice Age and waiting, with the infinite patience of geology, for the curious and the brave to come and read what is written there. Every dive into one of these systems is a journey through time, through the Ice Age, through the origin of life on Earth, through the first ecosystems that ever existed on this planet, and perhaps through the template for ecosystems that exist right now, in the dark oceans of worlds we have not yet visited. The blue holes do not announce themselves. From above, they are merely beautiful, dark circles in turquoise water, elegant and still, giving nothing away. But beneath the surface, beneath the halocline, beneath the sulfur clouds, in the absolute darkness of the deepest chambers, the planet is telling a story that it has been holding in silence for 20,000 years. And the scientists who descend into that darkness are learning, one careful dive at a time, how to listen.